Hey guys, in the previous lecture we introduced this idea of the Lewis dot model, and we saw how the Lewis structure, Lewis dot model, allowed us to predict molecular formulas for compounds and also see how those atoms are connected to one another in space. In this lecture we're going to extend the discussion. We're going to look at how those atoms are not only connected, but how they are arranged relative to one another in space, which is the topic of molecular geometry. Okay, so picking up where we left off, we have our Lewis dot model, right? And it describes a bonding connectivity for molecules, right? However, when we are drawing these dots and lines, we didn't really give any consideration to how those atoms are arranged other than to say, okay, we're going to put that more electropositive atom in the center, and then we're going to have groups attached to that central atom through these different types of bonding interactions. Okay, so in order to predict the shape or geometry of molecules, we're going to need really a single additional concept. And it's a concept that we're all very familiar with. The concept is that any electron group that we have around that central atom is going to repel other electron groups. So in this case, if we have a central atom and atom 1 here, and we've got 2 electrons involved in this chemical bond, covalent bond between these 2 atoms, that single bond is an electron group that will then be repelling all of the other electron groups around that central atom. And so the geometry that results for a given molecule is the result of essentially minimizing the degree of electron-electron repulsion between the different groups. Okay, so write that out here. Okay, so the shape of a molecule is the result of minimizing the electron-electron repulsion between the different electron groups. And it doesn't matter if our electron group is a lone pair or a single bond or a double bond, right? The different types of electron groups are all going to be repelling one another. Okay, and so the 3 types of electron groups we'll be encountering for the basic structures that we'll be examining here are either lone pairs of electrons, single bonds, or multiple bonds, so doubles, triple bonds, right? All of these represent a single electron group that will be repelling other electron groups around that central atom, and the minimum energy configuration that essentially minimizes the degree of electron-electron repulsion will determine our molecular geometry. So to illustrate this concept, I want to look at 3 compounds that we examined previously in the construction of the Lewis dot structure for, and basically build up this argument based on an electrostatic repulsion between the different electron groups concept in order to predict the geometry of each one of them. So let's start off by looking at the CO2 molecule. Now remember from our previous lecture, hopefully at this point you're nice and comfortable with drawing out the Lewis dot model for the CO2. For CO2 here, we are going to have a central carbon atom with only 2 electron groups, right? And specifically here, the electron groups are those double bonds. Okay, now the question we want to ask is what sort of arrangement in terms of, you can think about in terms of the angle between these 2 groups is going to maximize the separation or minimize the electron-electron repulsion. Well, many of you might intuitively and correctly identify 180 degrees or a linear arrangement of these atoms as being the optimal configuration. To look at that, what I want you guys to do is, and you can even follow along, I have a link in Canvas to a website that allows us to build a little representation of the CO2 molecule that looks right like this, where I'm representing with a purple atom here, carbon, and then each one of the oxygens in white on the end, okay? And so what this little simulation allows you to do, and you can build up any molecule you want, is allows you to sort of spin around and grab one of these atoms and push it, right? Move it around and see what would happen if we tried to alter the geometry. So you can see, and it's kind of fun to play with, that if I were to try and smash these double bond groups together, as soon as I move this one over to try and overlap with the other one, electrostatic repulsion pushes that other group away. And so that repulsion will continue until both of those groups are exactly 180 degrees apart. Okay? And so you can see then in this way that the minimal energy configuration for two electron groups is placing them all in a line. And in fact, we have a name for that. We call it a linear arrangement of atoms. Okay, so now let's go on and look at our next example here, which is CH2O, formaldehyde. And recall the Lewis dot structure looks something like this. And now we can see that we have 3 electron groups. All right, so we have 3 electron groups. So the question we want to answer here is, what is the geometry, right? Remember previously we found this one's going to be 180 degrees. We want to figure out what is the geometry, or what's going to be the bond angle between these different electron groups in this CH2O molecule. Okay, so to look at that, we're going to come back to our simulation here, and we find that if we add 3 electron groups around that central atom, then the electrostatic repulsion is going to be minimized if we each one of these electron groups are 120 degrees away from the others. Okay, so you can think about it as, we have 360 degrees of freedom here. And if we have 2 electron groups, as we saw previously, right, we had this sort of configuration. 2 electron groups splits that 360 degrees into 2 parts. Now we've got 3 electron groups, and it's splitting that 360 degrees into 3 equal parts, or 120 degrees for each. And once again, if I try and smash one of these electron groups close to the other ones, then the other groups respond by moving away. And as soon as I stop trying to perturb the molecule, things level back off to that 120 degree separation between each. And notice that if I flip this molecule to the side, all of these atoms are lying in a single plane. Okay, they're all lying in a single plane. And the vertices of each one of these terminal atoms, if we were to kind of connect the dots with those, we would form a triangle. So we call this geometric arrangement a trigonal planar arrangement. So if we come back here and we draw out the Lewis dot structure for formaldehyde, we are going to see a bond angle that is 120 degrees. And I'm going to put approximately 120 degrees. And this isn't something we're going to cover in any detail at the introductory level, but I want to mention that all electron groups are equivalent in the sense that they're all going to be repelling one another, but they're not equivalent in terms of the magnitude of that repulsion. So this double bond actually has more electrons. It's a total of 4 electrons, so it's a little bit fatter. And so there's a greater degree of electron density there. And so as a result, it's going to push away those single bonds a little bit more than what you would expect. So this bond angle would probably in reality be something slightly greater than 120, and then this bond angle down here would be something a little bit less than 120. Okay, so just keep that in mind. But what I want you guys to remember is that benchmark value of 120. So 3 groups are going to have a 120 degree separation, and for the linear molecule up here, we're going to have a linear molecule 180 degree separation. Okay, so we've now covered our first 2 basic molecular geometries, and for our last geometry here, we're going to look at the representative example, which is CH4. So CH4, hopefully everybody recalls, we've got a Lewis dot structure looks something like this. And once again, we're going to play this game of predicting what that bond angle is going to be between these CH bonds. So I want you to go ahead and pause the video at this point and come up with a prediction for that bond angle in CH4. Okay. Now, with your prediction in mind, let's go ahead and come back to our interface here and start building up that methane molecule. So, of course, methane has 4 CH bonds. So, put in the first bond, right, our first electron group. All right, we get a simple linear diatomic, right? We add in our second one. Just as we saw before, we have our 180 degree separation. We add in our third, we get our 120 separation, okay? And now essentially the moment of truth, okay? Notice what happens when we add in that fourth group. Okay? Some of you might be a little surprised by what happened here. Okay? It's very common because of our tendency to look at these molecules as we represent them in 2 dimensions, to forget the fact that we actually have a third degree of freedom. We live in a 3-dimensional universe, and so when you introduce 4 electron groups, many students will like to say, well, hey, they're all going to be 90 degrees apart, right? But because we have the freedom to move in all 3 dimensions, you can actually come up with a geometric arrangement that looks like what I have on the screen here, which places each one of these electron groups 109.5 degrees apart from one another, okay? And once again, this all boils down to solving a geometry problem. You've got 4 groups in space, you want them as far away from one another as possible, and you have 3 degrees of freedom, 3 dimensions to move around in, then this is the resulting geometry. And once again, if I try and smash one of these groups towards the other ones move away, and if I stop perturbing the molecule, everything just settles down at that 109.5. Okay, it's a little bit harder to see this one, but if I were to kind of set this molecule down and form a polyhedron by connecting all of these vertices of the atoms, right? The polyhedron would have 4 sides, and I'll try and show you on a slide here another illustration of that. But suffice it to say that polyhedron with 4 sides would be a tetrahedron, so we call this geometry a tetrahedral geometry. Okay, so if we come back then and we look at our Lewis dot structure here, we find that representing the Lewis dot structure as written leads us incorrectly to this 90 degree separation angle. So what I'm going to introduce here is a technique that we use to represent the 2-dimensional structure or 3-dimensional structures on a 2-dimensional surface. So what I'm going to do is I'm going to draw all of the bonds that are in the plane of the screen here with a line, as we would before. And then I'm going to represent the bonds that are going in or out of the board using a dash or wedge, respectively. So I'm going to represent a hydrogen atom coming out as this wedge, and then going back into the plane of the screen as a dash. And so if I map this back onto the little structure we're looking at here, notice that this first atom, hydrogen, carbon, hydrogen, are all in the plane of the screen here. And you can see in the 3D representation, one of the hydrogens is coming out towards you, one of the hydrogens is going back into the screen. And so those hydrogens are represented, going, back, and then this is going into the front. Right, popping out at you with that wedge. Okay, so to summarize what we've talked about here, basically we have 3 different broad classes of geometries. If we have 2 electron groups, we have a so-called linear geometry. We're maximizing that separation between the 2 electron groups. Sometimes a fun little thing to do is tie balloons together, and you can see where those balloons will rest actually are indicative of the corresponding molecular shape. And so the number of balloons just corresponds to the number of electron groups. Okay, so some examples we already saw about the CO2 example. Another example is BeCl2. All right, both of these cases, whether you have single bonds or double bonds, you have two electron groups and hence a linear geometry. Okay, we saw how if we add in an additional group, you get a so-called trigonal planar geometry. And the example we looked at was formaldehyde. And remember how, if we have all three, in the example of BF3 here, all three electron groups are exactly equivalent, then we get an exact 120-degree separation. But recall that I mentioned because that double bond is a little bit fatter, right, it's going to take up a little bit more room, and you're going to have slightly larger than 120-degree bond angles. Again, don't worry about the specific values here. Just keep that general logic in mind, covered in this little note. And then last, we talked about the tetrahedral geometry, and as promised, I promised a nice pretty picture of a tetrahedron. If we have 4 electron groups, then each one of those groups is going to be pointing towards a vertex of this 4-sided tetrahedron, or this polyhedron, which we call a tetrahedron. And the result is this, this 2-dimensional structure is represented, 3-dimensionally as such here. And to try and capture this same sort of format, I'm going to use a dash wedge model that basically allows us to look at that 3D structure on that 2D surface. Okay, now the last topic that I want to talk about is, what happens if we have lone pairs? Hey, well, remember that if I have a lone pair of electrons, that's still an electron group. It's still going to be exerting an electrostatic repulsion, with the other electron groups. So if we look at the Lewis dot structure for ammonia, right, we saw previously that we come up with a structure that looks like this, where we have 1 lone pair and 3 bonds. Okay, and so if we go back to our simulation and we build up a structure that has 3 bonds, right? Of course, 3 bonds gives us the trigonal planar, but then the ammonia, remember, has a lone pair associated with it as well. So notice what happens when I add in that lone pair. Okay, adding in the lone pair results in those other atoms being pushed out of that plane. Okay, so it's having a very marked influence on the geometry of the remaining atoms. And you end up with a structure that looks like this. Okay, now we still have 4 electron groups. So our so-called electron geometry is still tetrahedral. The number of electron groups determines that electron geometry. But now we need to introduce another term to discuss the actual shape of the molecule. And so we can click on that toggle here, and we see that the shape of this molecule, just looking at the vertices where each one of these terminal atoms are located, forms essentially a pyramid structure with a triangular base. And so we call this structure trigonal pyramidal or trigonal pyramidal. I've heard it pronounced both ways. Okay, and so really this comes down to just that presence of that lone pair, perturbing that overall structure. All right. And so that's what we're talking about here in the notes, right? We've got this lone pair pushing those electrons down, giving us a molecular geometry that's trigonal pyramidal and electron geometry that's tetrahedral. Now, of course, we could take this a step further, right? And, when we're really looking at the details of the interactions here, it turns out that these lone pair electrons are obviously not the same as a bonding pair of electrons. And if you look at this from an orbital standpoint, lone pair electrons are really more centered around that single nucleus, and they're really taking up more space. You can kind of think of the lone pairs as being fatter. Whereas a bonding pair of electrons, that electron density is spread out across both nuclei, And so as a result, these lone pair of electrons will actually take up a little bit more room. And so you'll see bond angles between the lone pair and the axis of the lone pair here and the remaining bonds. That would be something that's greater than 109.5 degrees. And then the angles down there between the NH bonds would be something less than 109.5 degrees. Once again, I'm not going to have you remember any sort of specific numbers, but just remember that general concept. Lone pairs take up more room. Okay, and now we could extend this even further and say, well, hey, what if we have 4 electron groups, but now 2 lone pairs? Okay, well, once again, we can go back to our simulation. Okay, in this case, we'll build up water, as we saw before, and we're going to take our central oxygen, put one hydrogen, put another hydrogen, and then put 2 lone pairs. Okay, so the introduction of 2 lone pairs obviously gives us a total of 4 electron groups, so the electron geometry will be tetrahedral, right? But now, looking at just the vertices of the atoms, all these atoms, they're lying in a plane, right? But because there's 2 electron groups pushing those bonds away from one another, and away from the electron groups rather, then we get this sort of bent configuration, where rather than linear, if we didn't have lone pairs, it'd be a linear geometry, right? But the presence of the lone pairs results in a bent molecular geometry, and sometimes you'll hear this referred to as a V shape. And of course, because those lone pairs are fat, they're taking up more room, then we typically see, experimentally for water, that bond angle will be, less than 109.5. Okay, so to sum this up, if you have a tetrahedral geometry, then you have a number of different options. We can have the electron geometry being tetrahedral, where we have all 4 bonding interactions, and you just have a molecular geometry, I'll denote it Mg, that's also tetrahedral, okay? But if we introduce a lone pair, right, then the molecular geometry is going to become trigonal pyramidal. And then finally, if you have 2 lone pairs, we're going to get a bent molecular geometry, right, with CH4, ammonia, and water as our representative examples of each one. Okay, so with that, we'll just sum up what we talked about here with essentially a single slide that gives you everything you need to know from this mini lecture, practically. We break down in the first column the number of electron groups, okay? And then the total number of electron groups is going to be the sum total of bonding and lone pairs. So columns 2 and 3 added together will give you the column 1. And the electron geometry here in this 4th column is identified by simply looking at the total number of electron groups. If you've got 2, it's linear. If you've got 3, it's trigonal planar. If you've got 4, then it's tetrahedral, right? But then the molecular geometry depends on the relative number of bonding versus lone pair electrons. So if you have a total of 3 bonding groups and 0 lone pairs, then, and this holds in general, if you have 0 lone pairs ever, then the molecular geometry and electron geometry are going to be the same. But if there's a difference, if you have even just 1 lone pair of electrons, then the molecular geometry will change. And you can see here, if you have an example where we have 2 bonding groups, which are, in this example here, sulfur-oxygen bonds, and 1 lone pair, then you'll come up with a bent geometry, molecular geometry. Similarly, as we saw with the example of ammonia, right, if you've got 3 bonds, 1 lone pair, you will come up with a trigonal planar geometry, and 2 of each gives you a bent geometry, illustrated by the example of water. Okay, so you want to be very familiar with, essentially the totality of this table, and you want to be able to take any of these simple molecules, construct a Lewis dot structure, and then use that Lewis dot structure to, and associated with these rules in this table, to be able to predict both the molecular and electron geometry and have an idea of the relative bond angles.